Hi, welcome to another edition of Calculus 2. Today we are going to talk about the dot product of two vectors and several of its applications. Let's go ahead and take a look at this interesting topic. So, dot product named because of the presence of that dot that you see in the notation. If I have two vectors and I want to take a dot product of them, I want to take a look at its definition and properties. Perhaps you have seen this thing in your other classes, most notably engineering physics classes. They do make quite a bit of use of this notation. The most famous formula in that context is that the dot product of a force and displacement is the work done. So let's go ahead and see what this is all about. So if I have a vector, let's take the vector A, and suppose it has components A1 and A2, and I have a vector B, and that one has the component B1 and B2. So in this case, the dot product simply product of the first components A1 B1 plus product of the second components A2 B2. So we are adding them up to get one single number out. This dot is not optional, it has to be written all the time. If I had my vectors in 3 dimension, the idea will be the same, just I have more components. So if I have these two vectors B1, B2 and B3, well then A dot B in this case would have been A1 B1 plus A2 B2 plus A3 B3. So again, these two are vectors. There are multiple components, but what comes out is a single number. Like in physics work or energy and such, is considered to be a single number. Okay, we have defined a new operation. We are going to go ahead and make a list of properties it has. It's quite easy to show that the properties of the dot product are, first of all, it is symmetric. Who you write first and you write second does not make a difference in the result. So we call this commutative, just as ordinary multiplication. Also, we have the associative property as before. So if I have 3 vectors, of course all of them either 2-dimensional, all of them 3-dimensional, we cannot do mix and match. We have A dot B plus A dot C. So what does this mean? On the left, I'm adding first, then dotting. On the right, I'm dotting first, then adding later. So this is going to be our distributive property. Then we have a form of associative property in the following sense. If I have a number, let's call it x, and I multiply it by A dot B, that is same as taking x multiplied by the vector A and then dot it with B, or take the vector A separately, take the vector xb separately, and then dotting them at the end. So this is a form of associative property, except that one of these entries is a scalar, a number, and the other two are vectors. Of course, it's easy to see that if you have a 0 vector in 2 dimension and you dot it with a vector, you are going to get 0. Remember, this is the vector 0, this is the just the ordinary 0. Or in your textbook, you are going to see this bolded 0, and the other one is the ordinary way. The other important thing to notice is that if you dot a vector by itself, what are you going to get? So if I dot A by itself, I get A1 times A1 plus A2 times A2, which is just the norm of A, or the magnitude of A squared. So to remind ourselves, this is if I take the norm of A and square it, I get the same result. This is important to remember. Okay. Now these are all straightforward to show. Let's just do a simple exercise. Suppose I have A is equal to 2, 3, minus 1, and B is equal to minus 1, 4, 5. So what is A dot B? So I have to multiply 2 with minus 1, 3 with 4, and minus 1 with 5. So minus 2 plus 12 minus 5, and that all adds up to 5. Okay, so far very simple. First major property of the dot product comes in the context of calculating the angle between two vectors. So angle between two vectors, let's separate. So this is the first major property we are going to mention. Meaning what? If I have a vector A and I have another vector, say B, well, they make an angle between the two of them. The question is, what's the relationship between this angle, the length of these two, and the dot product of them? This relationship can be written in a number of ways. One of them is to say that A dot B, the number A dot B, is same as length of A times length of B times cosine of the angle between the two of them. In other words, if you want to figure out the cosine of the angle, that's going to be A dot B divided by length of A times length of B. And of course, if you want the angle itself, then it is going to be arc cosine of this quantity. So any of these can be used to go after the angle between two vectors. Just before we go and explain where does this itself come from, let's go ahead and practice it in this context. Suppose I want to find out what is the angle between A and B. So over there I have A dot B. So let's rewrite this thing. A dot B is same as A times length of B times cosine of theta. Let's write it like that. A dot B in the context of this example, A dot B was 5. Okay, so that was 5. How about A? Length of A, we said from prior lecture, either square them and add them up, just like the Pythagorean formula, or you can do as we just said, A dot A is A squared, norm of A squared, so you can dot this thing with itself and then take square root. Either way, length of A is going to be, let's show the A, 2 squared, 3 squared, and minus 1 squared. Of course, minus becomes plus when you square it. This becomes square root of 14. B, it is minus 1 squared plus 4 squared plus 5 squared. So 25 and 16, so that's 41, and then 42. So what we have now is that 5 is equal to radical 14 times radical 42 times cosine of the angle. So of course I can turn it around. Cosine becomes 5 over radical. You can put them into one radical, or you can separate them into two. So 5 divided by this is the cosine of theta. Then you might as well delegate the whole thing to the calculator to find for you. Of course, you have to make sure which kind of a unit you want, degrees or radians or grad or whatever, and then you calculate your angle. So in this case, 5 divided by square root of 14 times 42, and I get something like 1.36. This would be radians. If this quantity negative, of course you're going to be dealing with the obtuse angle. If it is positive, it's an acute angle. If it is 0, the angle is 90 degrees. If it is 1, the angle is 0, and if it's minus 1, the angle is 180 degrees, or pi. So let's tabulate this situation. You can have two vectors going exactly opposite direction from each other, and of course the angle between the two of them is going to be pi, or 180 degrees. You can have the situation where the angle is obtuse angle. So in this case, a dot b becomes negative of norm of a times norm of b. In this case, a dot b is a negative quantity, but it's not as low as that. A very interesting, important situation is what happens if the angle is 90 degrees. Well, the cosine is going to be cosine of 90 degrees 0, so a dot b has to be 0. A dot b in this case is going to be 0. Another situation of interest, well, how do we know if the angle is acute between 0 and 90 degrees? In this case, a dot b will be positive because cosine of an acute angle is a positive quantity. And what if the two vectors line up, like a and b? So the angle in between these two is 0, so a dot b simply becomes length of a times length of b. So these are the 5 cases you might come across. Now, an important consideration is, where does this formula itself come from? Because we have a definition for what a dot b is. How do we know this is equal to that? That one requires a basic idea from trigonometry, the so-called law of cosines. That is what is at play here. So our formula is really nothing other than the Pythagorean formula in fancy new packaging. So if you remember from your trigonometry, you have something called law of cosines. When you are solving a triangle, the issue comes up that if I have a triangle, this side of length a, this is of length b, and this is of length c, and the angle between these two is theta. Then we have a formula which is essentially a modification of Pythagorean formula. Pythagorean says third side is equal to a squared plus b squared. That is good if this angle is 90 degrees, but when the angle is not 90 degrees, there is a correction here, which is minus 2ab cosine of theta. Okay, so that's a formula from trigonometry, very easy to prove by making a couple of uses of the Pythagorean theorem itself. Now what? Now we are going to adapt this thing for our situations. Okay, let's make a vector notation here. Suppose this is my vector a and its length is a, and suppose this is my vector b and the length of that is the little b. And then I can make a vector here too. Well, what is that? If I go minus b plus a, I'll get this thing. So this c is length of the vector a minus b. So here I'm calculating c squared. So here let's go ahead, start by a minus b and say what is that squared. That's my c squared here. Well, here we learned that very important new property is that the norm squared is the dot of a vector with itself. So that is what I'm going to do. I'm going to take a minus b and then dot it with itself, a minus b. Well, how do you dot? Essentially same as foiling idea that you had back in middle school. Same thing applies here by using rules of operating with the dot product. This becomes a dot a and a b dot b. Minuses cancel each other, so that's going to be b dot b, and then a dot b and a b dot a, both of them negative, and so I'll have minus 2a dot b. So a minus b squared is this c squared. So this is really c squared. A dot a, well, we said that is a squared. B dot b, that is same as b squared. And now I have minus 2a dot b. So this is same as that c. A and b are the same a and b. So this product has to be same as that. Therefore a dot b here has to be same as ab cosine theta. So a dot b is same as little a is the length of a, little b is the length of b, and we have cosine of theta. So that was a quick proof of the this very important property of dot product. To appreciate it, we need that background from trigonometry, law of cosine. So here we just showed that this is indeed correct. Okay, so we talked about 5 situations we can have, and the most significant of them, most important of them is perhaps this perpendicular vectors. Well, the issue is important enough to have lots of names associated with it. So we can, of course, we have the standard description from high school is that these are perpendicular. So but another word that's used is orthogonal. So more advanced text refer to this as orthogonal, and also sometimes the word normal is used. A vector is normal to another vector if their dot product is 0. So remember, perpendicular, orthogonal, or normal, these are sequence of wording that are used in this context, and you want to be comfortable with all the language. Okay, next up is how does this relate to our setup in our coordinate system? So let's go back to our coordinate system. Let's start with two-dimensional coordinate system. So I have my x and y, and you remember that these two were equipped with unit vector. We call this one I, and we call this one j. So these were the unit vectors. Now if I have a vector v, let's call it a. So okay, suppose I have a vector a. Well, vector a makes some angle with the x-axis. Let's call it x and y. Let's call this angle theta. Let's go ahead and write the dot product of a and the vector I. What's that going to be? We said the length of a, length of I, times the cosine of the angle between the two of them. Well, a dot I, this is length of a, length of a unit vector, well, by definition is 1, so it becomes a cosine theta. So if you want the cosine itself, you can say a dot I, and the denominator is just an a. If you're wondering what happened to other one, well, simply the length of I is 1. It's really down here, but you don't need to write it. You can write the same relationship for this angle. If you want to call it whatever angle alpha, then cosine of alpha is going to be a dot j over a. Well, in 2 dimension, these are complementary angles, and then there's no point in giving another name for this one. But in 3 dimension situation is more interesting. Suppose I have a 3-dimensional situation here. So this is x-axis, a y-axis, and a z-axis, and I still have my vector a here. Now this vector makes an angle with x, makes an angle with y, and makes an angle with z. So the situation becomes more interesting than what it was in the 2-dimensional case. Typically this is referred to angle alpha, this is beta, this is gamma, and we have the same relationship as before. Cosine of alpha is a dot I over a, cosine of beta is a j over a, and then we have, of course, cosine of gamma, that is a dotted with k over a. So ijk as before, this is my I and my j and my k. Well, really nothing new. It's just a name is going to be given to these things. Those are going to be called direction cosines. Direction cosines of v or of a, and our angles are going to be called well, direction angles. Alpha, beta, gamma are direction angles. Well, if you square these things and add them up, you get 1, the sum of squares of cosine square of alpha plus cosine square of beta plus cosine square of gamma is equal to 1. Is a little bit like the identity you have in trigonometry, where sum of the sines and cosine of the of a right triangle, angle of a right triangle is equal to 1. Now in 3D we have this version of it, which you can simply get by squaring these 3 quantities and adding them up. Okay, so these formulas are going to give us the direction cosines, and if you want to find the angle themselves, of course you said you apply the inverse cosine formula, just like we did here. So if you want the angle itself, you have to apply arc cosine or cosine inverse, and then you get your angles. If you just want the cosine, well, you stop at this level. So that was the simple case of the direction cosine of a vector. Next up, we come to a very important application in both mathematics, in physics, and engineering, which is taking a vector and splitting up to its parts. Since most of you are engineering students, let me just remind you, sometimes, most often in your physical or engineering classes, you deal with the inclined plane, just like a ramp behind a truck or something. And typically there is an object, a weight or a block on this inclined plane. Well, there's a force of gravity that's pulling this thing down, and typically you show that by weight F or W or something. So we have a vector here. So we have a vector, let's call it a vector F. Well, you want to find out how much force is pressing against the ramp and how much force is there to let this object slide up or down. So what you do is that you split your force to a tangential force, meaning tangent to the ramp itself, and the other component is going to be perpendicular to the ramp. Okay, so this is a big preoccupation in engineering, and the exact same thing happens in mathematics as well. It's just the same set of ideas apply in both disciplines. A force is given and we want to split it into along two perpendicular directions. So this is referred to as a projection. So somehow this reminds us of a projection, as if you are casting a shadow of this. So if you have a source of light here and this was an object and you were casting a shadow on this screen, you could think about this as the projection of F along that vector. So if I have F and I break it up into F1 and F2 here, then I can refer to F1 as F2 as the projection of F along these two directions. So suppose I have a, so let's go back to our A's and B's. Suppose I have a vector A. Now we are going to take that issue of ramp aside. We're just going to represent the ramp with another vector that's going to capture the direction of the ramp. So let's call this one vector B. So I have a vector A, which is representing the force, and a vector B that's representing the ramp. So what I want to find out is what is this vector. I'm going to call that, let's color it so it's clear what vector we are talking about. This vector, we are going to call that projection of. So projection of A on vector B. Projection of A on vector B. What is the formula for this? We have a simple formula. In fact, this is nothing other than basic trigonometry. You're taking A, multiplying by cosine of this angle, extended in the direction of B. We can wrap up everything in a very simple formula. It's A dotted with B divided by B dotted with B and multiply by B again. So rather crowded formula. Sometimes it's written like this, sometimes alternate form. So 5 items. 4 of them are B's, that is representing the direction of the ramp. 1 of them is the force itself, A. Okay, B shows up 4 times, A shows up once. Here's another style of writing this. It's sometimes you can write it A dot B over. We said further up that this is just norm of B squared. So that's another way if you want to write it in that style. So let's remind ourselves, when I do A dot B, I get a number. I get B dot B, that's also another number. Now I have a ratio of 2 numbers, so this is just a fraction. All we are saying is that the shadow of A on B is a certain fraction of B itself, and that fraction is given by this formula. Let's go ahead and practice this. Suppose I have A is let's say 2, 3. B is say 4, 5. Projection of A over B. So you don't want to get confused as to who is here and who is there. If you exchange the places, it's an entirely different story, as if you're taking the projection of the ramp on the direction of the force itself, which in physics wouldn't make any sense. But in mathematics, these A and B are just two vectors. You have to be careful which way projection goes. A on B is this formula. So A on B, I have to do the dot product of these two. So how do I do dot product? 2 times 4, 3 times 5. Denominator, norm of B squared, or the hypotenuse of B, whichever you want to think about it. So that is B dot B means 4 times 4. Better to write it as 4 squared, of course. It's the same thing. 5 times 5. And then this is a whole fraction. It has to be multiplied by B. You are in the direction of B. So I'll have 8 and 15. That seems to be 23. And this one is 16 and 25. It's 41. Oh, what did I do here? Let me correct myself. I wrote B here. This is of course 5 times 4, 5. No, this is a preferred way of writing it, but sometimes when you go on WebAssign, they just don't give you that much room. You have to compress everything inside your vector, in which case you make it ugly by just actually multiplying it through. 23 times 4 becomes 92 over 41, and this one becomes what, 115, I believe, over 41 again. But this is preferred when you're doing with hand calculation, because you're separating fractional stuff from essentially factoring things out. Well, we said there are two vectors here you are interested in. You're interested in this vector because you want to know how much force is pressing into the ramp. This is going to determine perhaps friction for you and such. The other one, F1, is going to be the force that's going to be responsible for accelerating this thing down the ramp. So each of these two play significant roles. So projection of A on B, unfortunately we just have one word for this. How about the other one? We have to improvise. So in this case, if I take A and project it on B, then the leftover of it is going to be in the direction perpendicular to B. Okay, so if I have one of these things, I want to figure out what the other one is. So in this context, we give priority to the direction of the ramp, and we get the projection of F to the ramp, and that's F1. How about this so-called normal force? I'll take the F and subtract that one from it. So if you want to call this thing, say, vector C, and C, what is C? Simply take that, remove this projection from it, whatever is left is going to be the normal projection. So it's A minus projection of A on B. So we do that by a simple subtraction as opposed to going to another formula. We could have made another formula like this, but typically we just subtract and find out what the other component is. Okay, that is for the projection, and then of course you have a lot of applications of these ideas in physics when you are calculating work and such, but we are going to leave that for you to so let me just mention some terminology. So let me just write it down. Projection of A on B, that is a vector component of A along or on B. So if you want to have the vector component, that's what you get. and the formula for that was again a dot b over b dot b times the length of b again. Sometimes all you want is the length of so if you want the length of the component of a along b, or they just simply refer to it as a component of u in direction of v, so in direction of b, so that's going to be a dot b, that's a number, divided by the length of b itself, which is going to be square root of this b dot b. So however you want to calculate it, that's going to be another style of so what is this one referring to? This is saying if I want to know how long this thing is, what's the length of the yellow vector, not the whole thing as a vector but just the length of it, we have a formula slightly shorter than the formula we had here. Okay, both of these are easy to show by applying a basic trigonometry, and I let you work on that. Okay, until next time when we see more applications of dot product, good luck and God bless.